Hi and good morning everyone. So today we're going to learn about Z transform. Okay, this chapter you will learn about the concept of Z transform and derive the Z transform from Laplace and Fourier transform, Z plane and polar form, the region of convergence, the type of region of convergence, the characteristic and the table of Z transform, and finally the solutions of difference equation and transfer function. Okay, Z transform is a counterpart of a Laplace transform. This transform is being used for solving variety of problems such as resistor, inductor and capacitor in analog system analysis by using frequency domain. So this is for Laplace transform lah. Laplace transform is used for analog system while Z transform is used for digital system. Z transform also can be derived from Fourier transform, which is same as Laplace transform did. It convert the difference equation system to a simple average equation to find the solution in one step. So if Laplace transform is used in analog system, Z transform is used in digital system. Okay, what about the derivation of the Laplace transform, yeah? So if Laplace transform is derived from Fourier transform. Okay, this is the review, yeah? So in Laplace, XS, yeah, XS equals to XT exponent negative ST dt integral, from negative infinite to infinite to positive infinite. So this is the Laplace transform. So apa tu? Yt equals to xt exponent negative alpha t. Okay, recalling the Fourier transform. Fourier transform is equals to xf. Okay, xf Fourier transform is equal to the integral of continuous time signal xt from negative infinite to positive infinite, negative exponent negative j to pi ft dt. So, yf equals to the integral of yt exponent negative j to pi ft dt. Yeah. And it is equals to integral of xt exponent negative alpha t exponent negative j to pi ft dt. Okay, this is because we have yt equals to xte negative alpha t. So apa tu put it in the equation, so it will be become like this lah. So as we know, s equals to alpha plus j to pi f. This is from the relationship of Laplace transform with Fourier transform. Kalau kita tengok dekat S plane, kita tahu bahawa that kita ada, we have for the S plane, kita ada sigma j to pi f. So this is S plane lah. S plane in Laplace transform. So that is why Laplace transform is equals to xs. S is alpha plus j to pi f, or alpha plus j omega. So if we put it in the bracket, so xs equal to xt exponent negative st dt. just change here as S. So yang ni pun sama. So we will get the equation for Laplace transform. Xs equals to integral of xt exponent negative st dt. Okay, so this is the Laplace transform equation. And for Z transform is originated from Laplace transform and it is used for discrete time system. So the definition of Z transform is xz equals to the summation of xn z negative n, yeah? Where z equals to r exponent j omega. So this is the relationship between the Z transform. So Z transform dia ada apa tu? It's if we draw at the S plane, so we have the real part and imaginary part. Sigma J 2 pi F or J omega. So R is the magnitude and omega is the phase. So then the derivation of Z transform. Okay, this one is recalled from chapter 3, sampling theory. In chapter 3, the pulse train signal looks like this. Okay, so this is pulse train, and this signal can be represented by equation x n delta t minus n ts. So xn, this is xn, xn domain n. So this is 0, this is 1 ts, 2 ts and so on. So that the apa tu the between the first train and second train is the time is ts, the duration is ts equals to ts. Okay, so this is the mathematical representation of pulse train. Okay, this signal will be used in order to find its Laplace transform. So if Laplace transform xs equals to the integral of xt exponent negative st dt. So xs is equals to the integral of, because we know that xt equals to this one line, this one. So this is xt. Okay, so xt equals to Sn delta t and ts. Yeah. We know that xt equals to sum of between n negative infinite to positive infinite. Xt equals to Sn delta t minus nts. So if we put this equation xt ni into here, xt here. So you will find that the Laplace transform xs is equals to sum of xn delta t minus nts exponent negative st dt. So it is an integral function from negative infinite to positive infinite lah. And xs, so what happened is xs is equals to the integral of xn e exponent negative sn ts. Why? Because in the discrete form, we define or assume a new variable will become z domain later as z equals to exponent sts. So when change sts exponent sts convert into z, then the new equation will become instead of you using s, now we will use z as the domain for the discrete time signal. transformation. So the transform now as xz equals to sum of xn z to the negative n. So this is the new one. Okay, the result is known as the bilateral or two-sided Z transform. And however, considering a causal system through the linear time invariant system, the Z transform will be represented as. So this is the equation for Z transform, where xz equals to summation of n from 0 to infinite xn z negative n. So this is Z transform. So derivation as the Z transform for causal system is equals to xnz to the negative n from 0 to infinite. The inverse Z transform can be described as this one. This is for inverse Z transform. This is for inverse Z transform. And to find the discrete time signal. Okay, so in time domain is xn. In Z transform, Z domain is xz. So yeah, xn and xz. So to change from xn to xz, we use this equation, Z transform. Okay, use this equation to find xz, and to get xn, use inverse Z transform. Inverse Z transform. If you have xz, you want to find xn, use inverse Z transform. If you have xn and you want to find the Z transform, use the Z transform equation. Okay, what is polar form? In Z transform, the time domain transform to Z domain. The time domain signal is mapped in Z plane. So Z plane is a complex plane that consists of real and imaginary part. Okay, now Z can be expressed in polar form. Real part, imaginary part, j omega. Okay, Z equals to R exponent j omega. Okay, and it has a 1 unit circle at R equals to 1. So, jejari when R equals to 1, we call it as a unit circle. Okay. So Z plan which conclude that Z transform in discrete time Z transform is equals to discrete time Fourier transform lah. Kalau dalam Fourier transform we call it as discrete time Fourier transform in Z plane. So this is the Z plane. So we have Z exponent j omega if R equals to 1. R equals to 1. Okay. Region of convergence, there are several types of region of convergence or ROC. The first one is inward ROC, and then we have another one is outward ROC. Inward ROC ni is that the region of convergence is inside the unit circle. Okay, unit circle R equals to 1 R equals to 1 kat sini. Jari dia ni equals to 1. Then the ROC is inward. Then we call it as inward ROC. Second one is outward ROC. And then we also have ring or donut shape ROC, where the ROC is between two between two between two poles. So in between two poles, the first one is inward, the second one is outward. Then it will, you will get the ring ROC. Yeah, ring ROC. Ring ROC. why region of convergence is important? Okay, the ROC is important because we want to know whether the Fourier transform sequence exists or not. So if it must be converged. If the Fourier transform exists, then the Z transform is stable. So we will know the from the ROC. The ROC is used to know whether the system is stable or not. If ROC does not include the unit circle, Fourier transform diverge and the Z transform is not stable. That means that if Z transform is Z transform, the stability is determined by the unit circle. ROC must include the unit circle. Okay, next we'll see the first example of Z transform.